Welcome to another CO2 Monday in the Refrigeration Mentor podcast. I'm your host, Trevor Matthews. And once again, I want to thank everyone for taking the time to listen, come and join these live events, listen to it on the podcast, check the videos out on YouTube. I really appreciate that. If you could share this with somebody else who wants to learn about refrigeration, wants to learn about CO2, that would be so awesome. As well as follow us on Instagram, LinkedIn, all the other social media platforms. Today, we got a great conversation. Super excited about this conversation once again because we're diving into something that is not new, but in the commercial refrigeration space is growing faster and faster. Artificial intelligence, machine learning, something that I got a lot to learn about because this is happening. And it's going to be good for the industry to really help us out to get better equipment, diagnose equipment better, troubleshoot equipment. And this is not something that's going to take away from what we have to do as technicians, engineers, as designers. This is going to help us make our industry better. And my guest today is a good friend of mine. We worked together back at Emerson years and years ago, and we met a few times. And today we're going to be diving in with my good friend Nelson here on artificial intelligence in refrigeration system. Nelson, how you doing, brother?
Good, Trevor. Thank you for having me in this podcast. I'm really excited to talk about these topics and to share my knowledge about this with all the people in the industry.
Yeah, and I really appreciate me and Nelson have been talking about this for a couple of years. He's been working on this for a long time, doing different projects, trying to understand how you can use data as well as data from what we can extrapolate to the point where now machine learning and artificial intelligence can help us out to either predict things, to help us in different areas. Nelson, why don't you do introduction of who you are, what you do?
Okay, right now I'm working in the artificial intelligence industry. Have a background in refrigeration and air conditioning. And also I've been developing some interesting tools to people who are enthusiastic as me in the refrigeration field. In this case, we designed this specific presentation for how to use this innovative approach of the artificial intelligence in the CO2 transcritical system troubleshooting for sharing our knowledge to all the people.
Yeah, and I do really appreciate that because this is what Refrigeration Mentor is all about, is helping share knowledge, helping others grow. And I know you love doing that too. I know for years we've been talking about share knowledge and you do a great job at it. Okay, well, why don't we just dive in, Nelson, and start learning a little bit more about this?
Okay, first, thanks to all the people that joined today. This is a brief presentation about one of the topics most relevant in the actual world, the artificial intelligence. In the next 45 minutes, a small introduction about the use of this technology for troubleshooting CO2 systems and how can we use this innovative approach in our field. First, we're going to review some relevant information about maintenance type and how the approach has been evolving over the years in pro of anticipating to the failures and decreasing the downtime of the equipment. In the first slide, we have the complexity. The maintenance has been evolving to fulfill requirements from the manufacturing. In our case, we are focused on manufacturing products, so the downtime is critical for us. First, we began with an approach about mass production, and then we change our paradigms, industrial revolution. The objective is change equipment and components that were wrong to fail. Then we move to lean manufacturing, which is a systematic approach to manufacturing and production on eliminate waste and maximizing efficiency. This is kind of more discipline because we are trying to focus our approach in the failures, but we are not receiving any feedback from the system. So we must trust that our maintenance windows are small enough to take advantage of the information that the system is giving us, but large enough to use in a good way for our technical resources. The next approach is the predictive maintenance. That is one of the topics that we are using right now in the market. And it takes relevance because we are trying to avoid unnecessary operation by installing sensors or systems that can bring relevant information to the table. In this approach, we try to look for tendencies and try to anticipate to some failures. We try to recommend some specific spare parts and improve the system efficiency as a global. We try to avoid some catastrophic events that can cause potential failures before it's too late. And the last approach is the prescriptive, is when we see the system as we are, for example, a doctor, an internist, seeing the system in a holistic way in which all parts works as one. And because this is something that all refrigeration systems have. All systems has a high dependency between different variables. So if we change the pressure, we change the temperature, we change the current, we change, a lot of data. This is an approach in which we take the measurement and taking all the data that has been possible. This is a problem that we can solve later, the amount of data. The idea is to pre-process the data in some way that can bring us some relevant results. The idea is to use these results as an input for a different system, in this case, artificial intelligence system, to obtain some results that has relevant to the maintenance guys. About money investment, we have to change our point of view from undisciplined approach to a more organized approach. We have to invest in the instrumentation, our learning process, and knowing all the time that this investment will decrease over the time. So because we are going to use the same instrumentation and knowledge, instead spending a lot of money and more spare parts, for example, changing equipment or working with optimal systems.
Okay, so I'm still learning about AI, and I know we're going to dive into it, but there's different approaches to it. There's like descriptive analytics, and then there's predictive, and then adaptive analytics. Is that kind of one of those approaches? Because my understanding is that in refrigeration right now, it's a lot of predictive analytics. Is that what you see in your studies for AI and refrigeration?
In the next slides, we have some approach, for example, to duplicate the behavior of the compressors, like a digital twin of the compressor of the system. And for the evaporator circuits, we have more statistical methods. We are trying to make some grades to the behavior of the circuits, and we can extrapolate this behavior to different system, CO2 or maybe HFO or HFC. It's the same behavior.
Excellent.
In this part, we have the component modeling. So we are trying to obtain some information. In this case, we have obtained some information about this compression and evaporating. We are building a digital twin of the compressor using the standard, the 540 coefficients. This is public information for all the people. I mean, you don't need to have a specific permission from the company to obtain this kind of values. This is free for everyone. And second, we need the evaporator nominal capacities of such condition. This is information that we can be obtained for the manufacturer manual or the catalog. And the other one is when data that we need, for example, the set points and hysteresis for pressures and temperatures in the suction, heat rejection, and the evaporation circuits. About some signals important to know will be the weather profile for the city, because all systems work in a different conditions. It depends of the city, of the place, the altitude, different conditions, because we are trying to expect some energy consumption and pressure values according to this approach. Other value is the isentropic efficiency for the compressors, which is a value of how close the compressor is about reaching the ideal performance without any losses. Sometimes we can assume this as a 70%. And for the evaporation circuit, the relative humidity level for goods stored, we have the opportunity maybe have a direct measurement with a instrument like thermohydrometer or something like that. All this data will let us to build an equivalent compressor. In this case, if we have a suction group, we can build a mathematical model. If we replace the mass flow, we have an equivalent compressor with the power of the compressor that is on in that moment. And for the evaporator, we have the equivalent load of that evaporator, and we have average value. This is a sensible heat ratio, which is related with the temperatures between the input and output of the evaporator coil, and also with the evaporator coil and the dew point temperature of the circuit. So we built a system with one specific compressor per suction group and some average evaporator in the evaporator side. That's the idea of modeling the system in a complex way, in a more simple way.
Yeah. Okay, so that's good. So people that are listening, Nelson has some drawings like mathematical equations up there. So you're taking these mathematical equations that you're building and you're going to match them up to what the evaporator and compressor manufacturers have in their published data. Is that correct?
Yes, all this is public data. I mean, we can
Yeah,
use
you can
that,
pull it off
and
the Bitzer website or the Emerson or Copeland sites or whoever the case manufacturer is as well. Okay.
yes,
So we're taking that data and then we're going to put it in, I guess, in some sort of algorithm where we're taking also the weather data, we're taking the humidity of the room, we're taking the power consumption, we're taking all this information because this is really good for CO2 because you're getting pressure temperature probes everywhere. So it makes a lot more sense and probably a lot easier than some other systems that are out there.
yeah, our idea is to build an average element. In this case, we are building a digital twin for the compressor and also for the evaporator. So this compressor will, the behavior will be like an stage compressor. For example, if we have 4 compressors in the suction group.
Okay, you mentioned digital twin a couple times. What do you mean? Can you just explain that to me one more time? What a digital twin is?
Digital twin is an element in which we can change all the parameters and try to obtain some data that can be relevant for us in the real world, but it will be dangerous to obtain this data in the real compressor. So we can change, for example, the suction pressures, I mean the ambient temperatures in the digital twin, but in the real compressor, it could be dangerous.
Okay, yeah. So that's kind of like the modeling of that you can change the variables to try to see what the outcome you would get.
Yes,
Yeah.
this is the
Yeah.
Okay. We are in the intelligence, the artificial intelligence world. We are using the normal data. So we are going to use normal data. For example, in this case, we have some pressures, the minimal pressure and the maximal pressure, and try to obtain a value between 0 and 1, because this is data that can be easily interpreted by our neural network to obtain some results. We can use the same approach with the voltages and current consumption. In this case, we have the nominal current and the nominal voltage, and we can analyze the variation of different systems. For example, in this case, if we have a system that has 226 volts in a nominal voltage of 220, we have an over voltage of 2.7%.
Yep.
So this is a value that artificial system can manage more easily.
Yeah, that totally makes sense because now you got information that you can use. It's usable information that I know that we're running at 226 volts, but really the nominal is supposed to be 220. And then from there, they can do that can go into other parts, I guess, of this prediction or analyzation.
Yes, that's the idea, to work with variations instead of like static values. It's better for, I mean, the intelligent system to understand.
Yeah, that makes sense because I'm seeing more and more systems, say case controllers, for example, they're not using static values for superheat anymore. The superheat will change because that's is going to work to become the more efficient for that evaporator as it changes. And so this is real good because it's better because that's real value, real time.
Yeah, the current consumption is a value that change over time. So we have an expected value for the calculation of that we can obtain for the nominal plate, or maybe from the manual of the compressor. We can use the same calculation to obtain similar results in the temperature side, or maybe this kind of transformation will let us to analyze data in a better way as an error value, or maybe as something that has an error from the expected. Okay, with the following, we have how the pressure controller works. We have the black line is the suction pressure for a specific suction group. There are two zones, one of activation, that is in this part, where the air compressors are engaged and over the high pressure in the suction side. And the other one is when the pressure is too low. So we need to release the compressor load because the mass flow is too high according to the actual requirement from the operators. This is the same algorithm that they use the projection side, but instead activation of compressor, we have the activation of the fans or maybe the BFD or BSD when the pressure is too high, and do the opposite, for example, when the discharge pressure is too low. Whatever will be the combination that we have, for example, in this case, we have some situation that can be possible. In this case, we have low suction pressure and maybe a high discharge pressure, which is a high ratio. And in different zones represent different combinations. So we have one area, the blue area, represents the normal operation, and the red area represents when the compressor, for example, the pressures are not in the right place. So we have two algorithms in this case. One that is focused in the discharge pressure. When the pressure is too high, it will give us an error, the high discharge pressure, and the low side, the low discharge pressure. And for the suction side, we have high suction pressure and low suction pressure. All these different combinations will give to the intelligent system and maybe to the technician relevant information about the situation and how can the technician solve the specific situation. If we have low suction and low discharge, it could be experimental factors such as low refrigerant, TXB, maybe a defective compressor, refrigerant line restriction, and all these combinations has different ways to approach to solve. In this case, we are building one algorithm. We are building the algorithm of pressure zone according to the envelope zone that is defined by the manufacturer. And also all this is public data for all people.
And yeah, and this is what I love about this. So everyone who's listening on the podcast, so Nelson has a chart up there that looks like an operation envelope of a compressor. You need to keep inside that operation envelope, and when you don't, you run into major issues. But right at this point, there are some manufacturers like Bitzer and Copeland and Duran and all these other manufacturers that put devices on there that will kind of protect some of this stuff for you, or at least shut the compressor down to protect it. So then as a technician, now you got to come in and you got to read some flashy lights or pull out your phone and look at some Bluetooth and kind of extrapolate some data and try to figure it out. But I'm assuming when we get into more of AI stuff, which I'm getting ahead of myself again, is that the system itself will try to make certain corrections on those points, because right now at this point you can get some of this stuff. You can go and you look at this core sense protection or this bits or IQ module, and it'll just say it's shut down on discharge pressure. You know your discharge temperature is too high, for an example. But I'm assuming that with AI, it will try, and then you'll get what you just showed. If you go to the next slide, it'll show you, okay, for low suction and low temp, it'll say, oh, you may have loss of charge. But I'm assuming with AI that it will try certain things to say, okay, well, we know it still has the charge in there, so that's not it. And it's going to pinpoint it a bit more. Is that kind of what AI is going to do in refrigeration?
Yes. For example, in this case, we have to train to show the system how the algorithm works. We have a high suction pressure with a combination of high discharge pressure. We have an index and a specific index, and that's all the system understands. If we have, for example, the index number 3, the system will know that he has this specific event. So the system, it doesn't know how to react for this specific situation. So that is the labor of the technician.
Yeah.
In some
That's kind of what's
cases,
sorry, Nelson. This is kind of what's out there now. Kind of this is what the manufacturers are working on now, right? Kind of this is kind of pinpointing the area now. A technician needs to go and figure it out when they get there.
yes, and some of the technicians may be kind of afraid because of the artificial intelligence, but this is something that works for you and can give us relevant information for how to diagnose the system. We have some specific situation that can analyze it for us in a specific way, but we are talking in this point about millions of data. So we can take one data for all the pressures. I mean, the pressures in maybe 60 data per minute, one data per minute per second. So we have a lot of data that is not possible to one technician to analyze at the moment. This is a tool that we can use. It's not something to be afraid. In the next algorithms, we have analyzed the pressure, but we must know that the compressor is linked to an electrical model. We have to analyze the electrical parameters because the compressor is linked to an electrical motor. So the imbalances in the load of the electrical motor can cause some effects in the current consumption, or maybe some imbalances that in the voltage can cause, if you have an voltage imbalance, that can cause the current imbalance, and in the same way around. From our point of view, the expert technician must adjust the limits of low and high voltage. We are taking this criteria from the NEMA, which is an association of electrical manufacturers, with a 10% of the voltage to be a low voltage value and a 10% over the average to have a maximum value. This is something that we can just in a physical control, for example, a voltage protector in the system, or maybe an electronics embedded in the system, like a core sense, or maybe an IQ, or some modes that can be found in the market. We have to build this value according to our knowledge of the parameters. This comes from the digital twin, the expected current consumption by the compressor. We have some values that comes from our technician, from our knowledge, and some others, for example, from the standard. In this case, we are using RE740 calculation. The idea is to obtain the parameters that gives to the artificial system, knows when we have some missing phase, some low voltage, some high voltage, when we have high amperes, high current detection, the low amps detection, and also the imbalance. Based on that, we can build what can happen in different situations. If we have high amps, it could be something related to the refrigerant, or maybe to the condition of the motor, or maybe the voltage that we are supplying to the compression, and different factors that we can manage.
Yeah, and that's key, because now you're taking all these different data points, and I like what you have there, like unbalanced voltage or unbalanced current. That's something that I didn't even think about when I started out in my first 4 or 5 years. Like I wrote it down, like I go do a maintenance, and then I'd write down, okay, 221, 222, 219. But it was something that I never thought about until years and years about, until someone actually mentioned it to me that knew about it. And this way it can take this data that a lot of people don't use and give you, I guess, a signal or a sign, or let you know that, okay, we have something going on here. Can the system adjust for himself or itself to make it work, or do we need to have someone come and take a look?
Yes, and all this data, the technician will have to take the pressure and the electrical parameters and the temperatures at the same time. This is not achievable by a only person, but for an intelligent system, it's something that is easy.
Yeah, no, exactly. Because that's the thing. You could be on a roof and you're getting pressures on a roof or temperatures on a roof. By the time you walk into the mechanical room, it's different. It has changed. Maybe a fan turned on and that wasn't on before on the roof.
Yeah, and this is the easy part. They obtain all the data that all the technicians knows, that the pressures, the temperatures, that parameters, but we are using the COP. When we are using the COP, we have different compressors. Or talking COP in a nutshell is the relationship between the effect of the compressor, the cooling effect in this part, and the power absorbed by the electrical motor that is linked to it. We have this effect compared to this one.
Yeah.
So in this pressure enthalpy diagram, we have an active system, and this is a condition that change over the time. We have to analyze when we have the cut with the saturation line, in this case, with the liquid one, and this is for the suction. So we have the saturation, We have to measure the pressure and the temperatures at these points. Why is better to use an intelligent system? Because we have these equations that is not something trivial for our technicians. We have to calculate some pressures with the flash tank, the quality, the subcooling. This is obtained within the ideal conditions or maybe the set points. So we have to calculate the suction pressure, the entropy, the enthalpy, the index of the efficiency of the compressor. This is when the things are not being easy. So we have the help, the software like CoolProof and Python and maybe the RepProf. It's software that is available for people, and we can use this software for obtain relationships in real time. This is the relationships for the sensors in which we can obtain the pressure of the flash tank with only a pressure proof, liquid line temperature with a simple NTC proof. And all this data can be compared with the expected data and know how the conditions will change in the system. If we calculate the COP and compare with the COP real, we can obtain or high value or low value. The difference with the different COP, it will be the lack of efficiency in the compressor or in the evaporator, or maybe we can obtain in the real system more efficiency in the compressor. This is something good or something wrong. Maybe we are giving more superheated refrigerant put to the compressor that can affect the global energy consumption of the system. So all those different situations are analyzed by the artificial intelligence system in real time.
Yeah. Over the last few years, I've been hearing more and more on coefficient of performance, the energy profiles. And this is where AI has started and really is pushing in for this predictive energy performance. And you'll see this in CO2 systems because most manufactured controllers, I've worked with all of them, when you get up into that supercritical and that transcritical mode, their controllers are trying to do the best COP, coefficient of performance, because when you're in supercritical or transcritical, your system is the least efficient, the least amount efficient. But when we get into more of the AI stuff, now we're having controllers to adjust things. And this is where I keep telling technicians and talk to more people, you got to learn about drives. You got to understand how they're working, because at this point, compressor can ramp up more, decelerate more, it can ramp up the fans more, spray more water if it needs to on the condenser, depending on the time of day, and actually change the settings itself instead of us having to do it.
Yeah, we have a higher return temperature in the compressor. We can have a higher discharge temperature that can be something that we must avoid in our system, because in that case, the condenser or the heat rejection will increase. So we can lose global efficiency in our CO2 system. This is the equation for the mass flow in the compressor. So this is how our software works. We have the equation, and we have to correct this equation according to the temperature in the suction and the quality of the refrigerant. We have the evaporator, so we can compare the temperature of the gas with the air, because we have some heats in this case. The heat gained by the refrigerant and the heat given off of the air. This must be equal. So if we model in these equations, we have some big equation that is related with the sensors. We have mass flow of the fan for the evaporator. We have the temperature that can be measured with two simple proofs. We have the humidity that we can obtain from an instrument or maybe from indirect measurement. And we have to calculate the enthalpies of the evaporator out, which can be measured with a simple proof, and the liquid line temperature. So all this equation can be obtained by physical signals in the system.
Yeah.
So
I've started to see over the last 5 years, like case controller manufacturers add a lot more sensors to their controllers. Started out with superheat controllers where they just had one pressure, one temperature. Then they have the air in, the air out, the, like you're showing, suction line or liquid line in, suction line out to gather more data.
Yes, it's to analyze the data and maybe to relate it with other podcasts that you were presented to different times. We are obtaining this COP, this mass flow index, and we are comparing if we will have more mass flow than we desire and or maybe less mass flow than we need in the system. More mass flow, it will give us problems. We have more refrigerant circulating in the system that is required that can cause blocking of the evaporators or maybe flood back into the compressor, and less mass flow in the system. We are risking the quality of the product that we are storing. And also we have less refrigerant, so maybe the compressors will not have the enough cooling for the labor. All these index are described. I developed one GitHub website for all the technicians, and maybe some enthusiastic about the refrigeration can consult some data in that website.
Yeah, definitely.
So
We'll have to send that to it. Let me know at the end so we can put it in the notes.
yeah, that's it. Yeah, at the end. Another issue that we have, you will see how the pressure behaves inside the system. So in theory, the pressure drop in the CO2 system will have only in the high pressure valve, the HPV, and in the evaporating circuits as well. Some lines such as the condenser, the heat rejection, or maybe the filters will have a pressure drop because it's normal in the system. That is something that in maintenance can result with the CO2, can result in the risky situation. Something like as simple as analyzing a filter. These two graphics that we will develop for this system, how it related the pressure at the suction manifold compared to the delta temperature in the filter, the difference across the filter. So we have a secure zone when the delta with the difference in the filter is low, but when the difference of temperatures across the filter are big enough, so we have replacement zone. So in the CO2 system is really relevant because in a big pressure drop in the system can cause situation like dry ice.
Yeah, so it's something that you need to understand, right? You get too low with liquid, you can cause dry ice. I
Yeah,
haven't
for
seen that though. I've talked to a lot of technicians. There's not many people that I've heard actual systems causing dry ice. So I've tried to make it in a system before, but I haven't I haven't had it. I haven't been able to make it.
for non-trained technicians can result in a risky situation because of the pressure or the fast temperature drop of the CO2. It can be very riskful.
Yeah. Well, definitely if they're replacing an evaporator coil, always after you evacuate, always open the suction first.
Yeah, that is something that can be documented in the system, or we can decide to build these kind of diagrams. This is the internal logic of the system, but this is something that can be used, for example, if the technician doesn't have any artificial system to transfer that data, maybe he can use these simple diagrams to understand what is going on inside the system. We can extrapolate this data, different systems, using the same principle. In the evaporator side, we have difference between 5.5 Kelvin, and in the gas cooler, it depends on the customer criteria. If the difference, a normal situation can be having a difference of temperatures between 7 Kelvin. That's something that can be built as a normal maintenance routine in the system.
Yeah,
So
and that's where you get a better understanding of how that heat exchanger is working with these different delta points.
yes, that is something that also is defined in the catalogs or technical information of the manufacturers.
Yeah.
That is something that we are giving to the intelligence system the tools to analyze our data. For example, in this case, we are not taking the approach of the artificial intelligence. So we are like building the real behavior. For example, this is the real behavior of the cold room, meeting something like grades to our circuits. So this operation can be done circuit by circuit, assigning some points. We have to compare the temperature profile of the system. This is the expected, and this is the real one. So if we compare the two graphics, we have some differences. The modal value, we expect all the values, for example, the temperature between this point, which is the highest point. We are pulling the product more than is required. We can have more energy invested in a low temp objective, maybe a wider temp range in the cold room. That can be something wrong for the product, and maybe some storage error. For example, some systems can have excessive openings, bad insulations, something that can be changed not by adjusting the controls, but talking with the people who is servicing the systems, maybe the technicians that are repairing the system, or maybe with the people who works in the installation, the sellers of the cool area or something like that.
No, I guess you could have a speaker on top of the glass doors in the frozen food section say, as the customer keeps the door open, you got to close the door. You got to close the door. You're causing me money.
That is something that can be changed by just talking with one person or a group of persons. At the end, it costs money to a supermarket.
No, for sure.
In the quality control area, they use these kind of equations that is not easy to build. We have the average data. We have some statistics that are not easy to calculate for technicians. So our intelligent system or the intelligent approach is to build this kind of graphics. We have an objective that is the set point of the system. And we have some limits that is the range of the control, I mean the thermostatic control. And we can see as graphically where are the most of the points in the system. In this part, where are the most of the points? So we have some behaviors that we want to have in our system. At the end, we can build this kind of graphics, for example, these heat maps of the circuits, which we can know with all the circuits at the same time, where are the temperatures in the real system. We can use both graphics at the same time. For example, we have a normalized temperature in this range. This can give us information about failures when the temperature rise up or rise down. And we have some behaviors. What is the most common temperature inside the cold room? We must use both data, for example, the time series and histogram. And how can we identify some failures inside the system? We can use the same behavior in the pressure side. For example, this is the gas cooler section. We can start to asking questions to ourselves. This noisy signal is normal in the high pressure valve, or maybe we have some high pressures in the system because of what? This is something that we can relate this kind of behavior with the real-time temperature outside the cold room. So all these assumptions that we suppose when we troubleshoot the system can be identified for an artificial system or an intelligent system or expert system in real time if we provide the correct data to that system.
Yeah, and that makes sense because what we're trying to do is get a better understanding while no one's there monitoring it, what is happening. And I like that last slide. Do you have plug strainers? Do you have overheating happening? There could be many things. The water regulating valve's not working. There's many things that could be happening and giving you more of an idea of what's going on with that system.
Yes, that's the idea, to obtain relevant information. I mean, for example, in this case, we have inferring results from the data obtained for an intelligent system that all compressors enough, one single stage, two stage, all compressors enough. So we can understand some technical information. Maybe our system is too big for the load that we can manage in real time, because in the 35% of the time, all compressors are off. So maybe we have a problem in the design area, or maybe we have two stage on in the 30% of the time, more or less. So we have a good design method compared to the suction group of the transcritical CO2. Other data that can be useful, it's when the system turns off one compressor, two compressor, three compressor, maybe the load profile is too much for that, maybe it's too low for that. That is something that can be analyzed for an artificial neural network. Can give us information how to adjust the timers in the controller. In the centralized controller, we have some distributed architectures, or maybe we have compatibility errors between the compression and the load type. For example, velocity process is different when we have a mid plant compared to a supermarket. Because in a plant, we have to reduce the temperature in a short time. In the supermarket, we have to maintain that temperature across the time. It depends not only with the knowledge of the process, but also with the knowledge of the system as well.
Yeah, that makes sense.
And about artificial networks. So this is the artificial neural network. This is a connection when we have different inputs, can be temperatures, as we said, normalized temperatures, normalized pressures, voltage errors, current errors, different that is related in a specific, we have to adjust the way in which different inputs interacts with each other. This is inspired in the neurons of the human beings and the human brain. We can put different hidden layers. It depends of we relate the pressure and also the voltage and the current. We can have this specific neuron taking information of how the pressure is related with the current. Pressures goes up, so the current will rise up, something like that. We have different relationships and the system will adjust the different relationships across the time. And the system, the artificial system will adjust all the weights inside the neural network according to a method called backpropagation. We have some data that we use to train the neural network, and we must know the outputs of the neural network. And in that case, we are adjusting this output, we are adjusting the system in this case. We have these inputs, the pressures, the errors, and the idea is to obtain from the system when we have the envelope error, the voltage error, the performance, mass flow, and component, as we see in the previous slide. This is the proposed recurrent neural network. We are using this architecture. In this case, we have some interesting data to obtain. How is the precision, the recall, and some other scores for the neural network. So we are using data, historical data, in which we know the outputs and we know the inputs. So we have to analyze one by one the data that we are putting in the artificial neural network and try to obtain the highest values in this, for example, in the precision and the recall. We are using the recurrent neural network because it requires to restart its memory. So in some case, if we correct something like we change a filter or maybe we change a compressor, the neural network will not have that kind of behaviors to diagnose the system in a future times. The idea is to obtain data like this. This is data from 100,000, no, 20,000 data, sorry, 20,000 data in a real time from a system that is data from 3 months.
Do you mean 20,000 points you were taking of data?
20,000.
20,000 points.
20,000. So we have in those points a high probability of having high suction pressure and high discharge pressure. With those data, we have low current draw. It can be something related with the refrigerant or maybe with the condition of the compressors. And we have only current unbalance detected. That is something that can be extrapolated for the data, that can be obtained from the data. So we have current balance. And about the COP, that is something that is not easy to see in a system. We have low COP, the evaporator, and high COP, a compressor with a high probability. In our technical knowledge, we can see that, or we can assume we have a good level of superheat in the evaporator and maybe wrong insulation failures or maybe a reheating in the suction of the compressor for this group. This is something in the side of the filters. We have in this graph 60% of probability of having high pressure drop in the liquid line filter. So we are diagnosing the filter without taking some invasive measurements in the system. We are taking some information, relevant information, only with the data that can be obtained from the controller or maybe a different sensor system that we have in field.
Okay, so that makes sense. So that system that you took the actual data on, it must have been a large system to have that many points, to get that many data points.
Yes,
Okay.
If we have more information, we can surely have more results and more relevant information, more relevant results in the output of the system. In my case, I built this element in order to catch all the systems signals. For example, I have information from currents, from temperatures, voltage, pressures. That is something that brings information to the neural network. So all the layouts and the information for building something like that, it's in my website.
What is the website?
It's a GitHub. I have the information in another slide.
Okay, beautiful. So this here, you built this where now it's going to take this data, you'd put it on a system, I would guess. Either can it take data that's already in a system instead of you having to add extra sensors? Will it pull data through BACnet, Modbus, anything like that? Or do you have to physically use these sensors?
Yeah, if you have a centralized controller or maybe distributed controllers inside your system, wonderful. You can obtain all data in real time and put it in an artificial system to analyze and obtain results.
Cool.
But in my case, I don't have access to a system, so I have to build one and obtain all these signals in real time.
So you can keep going. So you'll take what it'll do. You'll have data. It'll take some data. It'll look at the data. Then it'll adjust some data if needed. Will it actually? Can you make it manipulate the system if needed as well?
Yes, you are teaching the system. So that is, in this point, it's important to have expert knowledge from our technicians. So this is something that is not focused in replace the technicians. This is something that is scope is to help the technicians and to reduce the time in we have some relevant diagnostics from the systems. This can be misunderstanding for something that is not maybe according or maybe in a good way with the intelligence system, with the artificial intelligence, but this is something that works for us. We are not working for the artificial intelligence. We can use all the knowledge, all the velocity in which we can obtain relevant data to increase the diagnostics. I mean, the real-time information that can put in the customer to avoid this food spoilage or maybe high energy consumption. That is something that can bring relevant information to the table.
Well, it'll help them understand, well, you need to do maintenance. Like that's one of the biggest things I hear from contractors and technicians is that like they need maintenance done or it's going to cost them, it's costing them money, and they don't see that because refrigeration's in the background. They're looking at the front and oh well, refrigeration costs what refrigeration costs, but when you can save tens of thousands of dollars a year, that's a big part of a end user's bottom line when you can use a device to help show them and prove to them, that show them the data that like this can be done in a different way.
Yeah, and instead wasting money in energy consumption, you can invest that money in training, in instrumentation, and something that can bring a peace of mind to contractors and customers. Some items that I would like to mention, saving energy is not something that is industry process dependent. We can achieve that even in our homes. For example, building instrumentation or maybe changing the practices, as we mentioned, something that is as closing the fridge door. I put this in bold because we try to underestimate the knowledge of our technicians. The knowledge of our technician is a great way to train an artificial intelligence system. Some people install a lot of controllers inside the system and never use the data. So data without purpose is worthless. To finish with this catchphrase from Lord Kelvin, if you can measure it, you can improve it. We are going to start using that data and improve our troubleshooting routines in the different processes.
Yeah, and I totally agree. I think these are devices that can really help technicians fix a problem the first time, find the root problem out a lot of the time, because I've seen that time and time again when we did work for the compressor manufacturers, compressors coming back and there's really nothing wrong with them, where things like this, devices like this could really be a game changer for technicians out there or really help assist them, right? It's a great tool because we still, as technicians, we still have to have the knowledge of how to use the tools, how the system works, and this is just going to advance the knowledge of those technicians a lot faster.
Yeah, that's the idea. And finally, we're showed all the people in the podcast where they can find the information. This is the access to my different networks. And if you are interested, or maybe you want to complement the information that we put in the podcast, you can look for Symbionte on GitHub. I have a website in GitHub that is something that is public. In this one, I develop some of the internal information that is in the algorithm and also in the prototype of the system that I built. So this is all this is
Wow.
public information. For example, this is the device. Some technical information, for example, if you want to diagnose some systems in real time, for example, in how to diagnose or how the system diagnose the superheat, you take the pressure, application, temperature, refrigerant, and this is how the system works with that. And what are the effects, for example, of having high superheat, maybe low superheat? All this is public information for just to give back something to the people that once in a time told me something.
That's amazing. That is amazing that you did all this to help technicians out there. I'm going to have all this in the description. You definitely have to check out Nelson's website here to give you an idea on how to help you build these. You need to definitely reach out to Nelson on this. That's a super cool device. How many devices have you have one built for your own? And I know you spent a couple of years doing this. This is something
Yes.
fantastic for the industry. What's the best way that people can reach out to you? I know you had the slide up there, but what if someone wants to reach out to you, find out more about what you build, your artificial intelligent design?
Yeah, if people wants to reach me through my social media, maybe my email, and maybe the easiest way is through LinkedIn. If someone wants the data or maybe the blueprints for the device, can write me an email. Sure, I hope I can give you all the information.
Wow. Well, helping technicians build these devices so they can create them for themselves. That's amazing, Nelson. I want to thank you so much. I've learned a lot here today. I know there's a lot more for me to learn because we're just getting started in the refrigeration industry with more artificial intelligence and machine learning. I want to thank you so much, Nelson, for coming on CO2 Monday. And I want to thank everyone for taking the time to hang out with us as well. And we'll see you at the next CO2 Monday. Thanks, Nelson.
Thank you.
Hey, thank you for watching this video. I do hope it is bringing you a lot of value. If you are looking to grow and build your refrigeration teams and want them to learn CO2 refrigeration, head to the refrigerationmentor.com website, click to contact us, and let us know how we can build a culture around training inside your organization. Let's get a conversation going.